So hi everyone, thanks so much for joining us. Today our speaker is Pratik Nandy from India. Pratik is our collaborator and he's currently visiting the city. Pratik is finishing his PhD at the Center for Energy Physics at the Indian Institute of Science in Bangalore. He will be starting his postdoc in September at the Yuka Institute of Theoretical Physics at Kyoto in Japan. And he'll be joining what is called this extreme universe collaboration. And Pratik is interested in quantum field theory, quantum many-body systems, and holography. And specifically, he's working on the applications of various quantum information theoretic tools, such as complexity, entanglement, etc., in these areas. Now, before I hand it over to Pratik, please note that we'll have we'll have the last 10 minutes for questions. Also, you are welcome to ask questions in between. Also, we have an interactive session in Kumo space after the talk. The link is already in the poster, and also Renee has added the link in the chat box. So I'm now giving it to Pratik for his talk.
Okay, thanks Sajid for the introduction, and thanks for inviting me and giving me the opportunity to present my work here. So I will be talking about some recent works and progress on Krylov complexity, which has gained much. It's quite an important tool in recent times, both in condensed matter systems and also in high energy physics community. So let's first to understand how this quantum information actually plays different roles in many different kind of systems. So it's basically one of the hearts of the many confluence of different ideas. For example, we can start from quantum gravity, cosmology, and there are also applications, very much applications in quantum many-body systems. And recently one is gaining much attraction, like in the machine learning, studying the phase transitions and many things. So the quantum information lies basically at the heart of these small things, and there's many things and studies one can do using these ideas of these probes. So for the holographic side, one usually studies the so-called the Adcf Prediction. This is basically the anti-de Sitter space and conformal field theory correspondence, which basically there's a kind of dictionary. So there is a two space, one is Adf space and one is the CFT. So there's a two kind of dictionary. So some language you can speak some computation doing Adf space, and similarly you can do some computations in CFT language, and you can try to correspond as how these two things are equivalent. So this is how the quantum information actually comes into quantum gravity, especially in terms of the entanglement and the complexity in specifically. And there's also applications that I've said this applications many-body system. So this is a very crude picture, very incorrect picture of so-called known as the butterfly effect. So this is basically one of the ideas of the quantum chaos that I'll be going to talk about in later. So in quantum chaos, so this is so-called the butterfly effect. So let's start this. Okay, so the outline of my talk is first I will discuss about the complexity. It's a very brief introduction about complexity. Then I will talk about some understanding of chaos and try to connect how the talk is the main motivation of this talk, how to understand this chaos using the ideas of complexity. So the leading role will play is the operator growth hypothesis, basically, which tells us how this operator growth operator grows in your something known as a Krylov space, and so from that we can associate some information theoretic known as quantities like Krylov complexity, and usually one can perform some notion of Lanczos algorithm, and we'll see some examples of some spin systems specifically. I'll not talk about any holography in this talk for today's talk, so we'll only focus on many-body systems, spin models, and things. And finally, and later on, we'll also go to the open systems. So the first part of the talk will be on the closed systems. Then I will talk about briefly on some open quantum systems that we're currently working on, and I'll conclude with some outlook and some summary of the talk and some recent works that one can do using this language. Okay, so quantum complexity is basically a notion of is actually stems from this quantum computer science community, which is basically tells about how is how difficult is if you want to build a task, or if you want to obtain a task, how difficult is to implement that task. So suppose if you want to go from A to B, you can go, it's very simple, just this way, or you can take some different route, many different route, and go to the center of B. So complexity the complexity actually tells what is the simplest way to go from one point to other point, or from one task to another, one point to other point by some task, some whatever task you can, there are many tasks you can associate it with. So in the quantum language, we want to, that our task is to building some unitary operator. So we'll some initial state, there's some final state. So we implement some unitary gates, unitary operators to go from this operators to this operators, and this is our task. So we want to minimize the cost of this unitary. That's the task, and the complexity is basically associated with this task, the building of this operator. So you can also tell it about this. This is some operator complexity. If you are computing this operator, the complexity of this unitary operator, or you can also talk about this state complexity, which is basically the how from this state to go to this state. So basically, these two languages are basically interrelated, and there are some notions of this state. So this is the complexities, and you can also build this unitary operator in some IBM quantum experience. So this is basically very nice feature of quantum computer, this IBM, that allows you to build the gates that you like to. This is basically one of the circuits that some random circuits you can build, and this is kind of gate. So this unitary you can build up some simple single gates, or maybe in a multi-channel gates. So this is basically 2-qubit gates. These are number of qubits. So this I, J, K are the qubits. So this is a 2-qubit gates. This is also 2-qubit gates. All gates are 2 qubits in this. Then you can also have a 3-qubit gates, many qubit gates. So in generally we'll prefer to stay on the 2-qubit gates because they are very simpler to build and easy to build. Okay, so this operator complexity is one of the main focus in our ongoing discussion, but we'll see this is not exactly that what I've said, but the ideas are very similar in that sense. This difficulties of implementation. Okay, so as I said, that one of the goal is to using this understand this quantum chaos using the ideas of complexity. So it has been for a long time. This has been studied in many different contexts. The complexity that I have previously talked about is known as the circuit complexity. So it has been already studied about this operator growth using the circuit complexity, specifically known as some kind of version of precursor complexity, and it's mainly focused on the holographic tensor networks, quantum channels by these people, and also you can also study this in some simple harmonic oscillator, inverted harmonic oscillators, and many simple quantum mechanical systems. Also on some cosmological perspective, this is already studied. So here there are some different regimes of cosmology. And you can study the quantum chaos version of quantum chaos, how these regimes are, whether these regimes are quantum chaotic or not, using the many ideas of different notions of different information theoretic measures. For example, one of these is the complexity. Okay, so but let's focus on what's the classical chaos. So this is basically what I've studied is the quantum chaos. So I'll go to the quantum chaos, but let's first study what is basically known as classical chaos. So classical chaos is basically if you have a two trajectory, you start from very nearby points in your classical phase space, and you just deviate some perturbatively from the initial points, and you look how the trajectory looks like after large time. So this is it. This is your initial perturbation. How the initial perturbation affects your late trajectory. That's the main ideas of classical chaos. If the systems go this deviation, the late time exponent grows exponentially. This is known as a classically chaotic system. So you describe this is by some Poisson bracket, because if you expand this Poisson bracket, you'll get exactly like this. So this exponential is exponential of t in time. This lambda is known as a classical Lyapunov exponent. So there's also a version of quantum Lyapunov exponent, but we'll take these two things are very different. It's not, you could just take the classical exponent, just quantize it. It's not that quantum Lyapunov exponent, but the classical Lyapunov exponent is how your Poisson bracket, grows over time. If it grows exponentially, and this coefficient is known as the classical eponym exponent. So how do you quantize this Poisson bracket? You just Poisson bracket, you quantize with the commutator. So when you quantize with the commutator, and these commutators, these operators are the Heisenberg operators, and this is basically known as the out of time order correlator. So you can compute this quantum commutator and take some thermal average, some exponential minus beta of Hamiltonian with this thermal average, and what you got is known as out of time order correlator. So you can, instead of position and momentum, you can also take any generic two operators, not in position momentum, but any two generic operators under such evolution of this kind of Heisenberg evolution, and this is known as the out of time order correlator. Like the Poisson brackets grows exponentially over time with the classical Lyapunov exponents for the classical chaotic systems, you will also expect your OTOC probably will also go like exponentially for if the system is quantum chaotic. This is your direct generalization from a classical system to quantum system by the semi-classical ways, because you just take a semi-classical system, right? So these quantum lambda area is known as the quantum Lyapunov exponents, and your n is the degrees of freedom. So this quantum Lyapunov exponent actually is a lower bounded, is upper bounded. Sorry, it's upper bounded by the temperature of the systems, which is divided by 2 pi. This is known as this very famous chaos bound, Madhusana-Shenker Stanford bound. It cannot be anything, but it is bounded by your temperature. This quantum Lyapunov exponent. And when this OTOC, initially the OTOC, when the OTOC becomes an order of a number, so if the OTOC is some order of a number, you can directly compute how this Lyapunov exponent becomes. So this basically, this is the order of a number. This is nothing but this logarithm scales logarithmically with your degrees of freedom. This time scale is known as a scrambling time. So this time scale will be important in your later discussion in Krylov complexity. So what does it mean? So in the classical system, we have seen that the exponential growth of your Poisson bracket is a signature of classical chaos. But the quantum system, you can also expect the similar. So you for example, you just declare that exponential growth of the OTOC may be a signature of quantum chaos, because you directly generalizes from the classical mechanics. So this is a long time it has been believed that exponential growth of what is indeed is a signature of quantum chaos. But actually this statement could be misleading. There are some recent papers which has been shown that there exists some integrable system which are not quantum chaotic that can also show some exponential growth. For example, one of the examples that I'll discuss in later in the context of Krylov complexity is the LMG model, the Lipkin-Meshkov-Glick model. This is a classic speed system. So here your OTOC. So you have in the system, you have some classical saddle point in your classical phase space. This system is integrable, but in the phase space, you have a classical saddle point, and due to this saddle, this OTOC grows exponentially. So these are the finite size effects. So we just treat the up to this linear growth up to the scrambling time. So you see the spin. This S is the number of spin. So here this is not a many body system. This is a single body system, but you are enlarging your Hilbert space by increasing the degrees of freedom. Increase the number of the spin operator, the value of the spin operator. So you take some initial operator Z and you compute the OTOC. You see that OTOC grows exponentially in spite of your system is an integrable system. So this is a classic inequality that these people have proposed, and you can also compute to see that this OTOC grows very close to this square root 3, which is what you can get from your classical Poisson, classical Hamiltonian equations. Okay, so I will come back to this problem again when we discuss the Krylov complexity, how this Krylov complexity matters for this system. Okay, so beyond this OTOC, there are well-known probes, like for example, this level statistics, which also probes this quantum chaos. So this has been for a long time that people used to study this level statistics for classical spin systems to understand the quantum chaos. So this is this is one of the model that I will take. I'll discuss this model from the end this is the only model that I will discuss, the spin system. So this is a Hamiltonian. This is known as transverse field Ising model Hamiltonians. This is a Z are just basically the Pauli Z, and this is a Pauli X. And these are for this system. If G equals to -1, H equals to 0, the system is integrable. Actually, the system is integrable for any G if H equals to 0, but I will take just a one limit of this -1. And the G, and for non-zero H, the system is chaotic. So I will take this limit as some maximally chaotic limit of the system. So you can plot the level statistics of the system. So this S is the energy level between the separation between two energy levels, and PS is the probability. Okay, so when your system is integrable limit, this follows the Poissonian distribution. This is exponential decay of your probability. And when the system is chaotic or non-integrable system, the system follows something known as Wigner-Dyson distribution. So this is a classic example how you tell your system is whether this system is integrable or system is chaotic, just by taking the Hamiltonian and plotting the energy level statistics. But there's some catch. So unless your Hamiltonian have some specific symmetry, then it would be very problematic to plot the to show the level statistics, because when you have some symmetry, you have to remove all the symmetries of your system to get the level statistics, unless it always shows Poissonian statistic in spite of this, whether a system is chaotic or integrable. So you need to remove all the symmetries, then you have to plot this energy level statistics, which is in general very difficult, because unless your Hamiltonian is very simple, you do not know a priori what the symmetries are, when specific spin symmetries and other symmetries. So although this method is quite generic and it can in principle apply to any Hamiltonian, but it's a bit a tricky thing to apply for in generic cases or any non-trivial Hamiltonian. So we we are finding some better probe in this age, whether this is possible for without removing the symmetries and things. And also one of the inspiration is to study this operator growth in the holographic picture. This picture is not very you can just extend this thing to holographic very smoothly, but we want to find a better probe which can also study holographically. So also that can have some understanding of this level statistics as well. So one of the probe is this study the operator growth. Suppose I give you this Hamiltonian, again the same Hamiltonian, and we start from a simple operators, the one-side operator. So this is a many-body system. In principle, this is a many-body system. It doesn't have many-body system, so we're not taking any semi-classical limit. It's a very generically a quantum system. So you start from n lattice size, and you start from a very simple operator, the first lattice size. Suppose you start from this. So you want to understand how this operator grows over your full system. So under this time evolution, your simple operator actually becomes a very complicated operator, because you take the Heisenberg time evolution, which can be expanded in terms of this Baker-Campbell-Hausdorff formula, and you see there are kind of nested commutators appears after each term. So these nested commutators, actually, if you compute this Hamiltonian and take the simple Z1, these operators and these operators are becoming one side, then two sides, and three sides, and many side operators. So it not becomes very simple and localized. It spreads the whole system. So for short, I will denote this Liouvillean as some Hamiltonian, which is just in commutator with some product, some commutator with some operator, any operator. So this will be important in our later discussion when discussing about the open system. Just to remind you. So for example, if you evaluate the commutator, you can write this expansion of the operator in terms of the exponential of this Liouvillean acting on this Z1 operator. And this, for example, if you take this Z1 as a simple lattice, just one qubit lattice operator, over the time evolution, you see you can get it has been supported on many different sides. So it is increasing support of many operators. On your time evolution, it becomes complicated. That's how the operator grows over your lattice sizes. Okay, so you want to understand this in terms of some language. Okay, so you can expand this operator, this is a time eval operator in terms of some nested commuters, some basis of your words. So you want to construct a basis. So these are the bases that you are constructing. These are the bases. So the increasing, non-increasing commuters are the basis of your expansion. So any operator you can write in terms of acting on the Liouvillean multiple times, because the Liouvillean is basically the Hamiltonian with this operator commuted. Then you can act the Liouvillean again. Then you can nested commuters, going nested commuters. So basically, this is the giving you the nested commuters. If you start from initial operator O0, this is basically the Z1 in your previous case. But the interesting point is the previous studies of complexity that I have talked about in the first slides, the circuit complexity. You don't need any arbitrary choice of basis gates. The time evolved basis, the nested commuters, by themselves forms a good basis for your expansion of your operators. That's the one of the important to understand, that this method that I'm going to tell is very generic and very interesting on its own right. And it's also the basis that is more natural, because you don't need to define any basis states, any giving any penalty factors, or any sort of arbitrary. No, there is no sort of arbitrariness in this language as far as the basis gates are confirmed. Okay, so but these basis gates may not be orthonormal, because these sets, this A is Z1 and these sets may not be orthonormal. So you want to find an orthonormal set of bases made by these nested commuters. So what you do is this Gram-Schmidt orthocorrelation is a well-known procedure to make some basis. So this is your this basis your non-orthonormal basis. You apply some Gram-Schmidt orthogonal transformation and make some orthonormal basis, so that this orthonormality is basically it's 1. And you define your inner product by this method. This is known as infinite temperature inner product. So at this point, I would like to point out, so there are indeed some ambiguities about defining this inner product. Although there is no ambiguities about this choice of basis gates, but there is indeed some ambiguities of this definition of this inner product. You can take many different kinds of inner product, but for the moment, for the purpose that has been used many literatures in this kind of natural inner product known as Whiteman inner product is one of the inner product that is useful, and you could also generalize to the finite temperature case also, but I'll just primarily focus on the infinite temperature inner product. So there is no beta in this picture.
So Pratik,
Yeah.
sorry, there is a question from Ilya. Do you want to say your question?
Yes, sorry. Hi, why not just apply, if you're interested in operator growth, just a Lieb-Robertson bound?
Yeah, so for the Lieb-Robertson's bound, you have some spatial separation, right? So there's some notion of butterfly velocity. So there's two operators growth spatially, and you can also, in principle, apply the Krylov basis sets that I'm going to cover in that language. But currently, I'm only talking about this time separation. So there is no butterfly velocity in that picture, in the bound of this Lieb-Robinson things. But you can in principle do that thing. If you have a spatial separations of this operator, so time and x also enters in your the definitions of your Krylov complexity that I'm going to talk about. But I only just focus on the time separation between these operators. I mean the growth of this thing is only the time separation. Is only, there is no x dependence here. As far as
I mean, I think he's happy.
Okay, should I proceed?
Yes, please. Yeah.
Okay. So as I've said that
Click the actual size.
Oops. Okay, sorry. Yeah, sorry about that. So as I said that we need some orthonormal basis for this procedure. So how do you create the orthonormal basis? The natural notion is the Gram-Schmidt orthogonalization procedure. This is basically known as the Lanczos algorithm. One of the algorithms is known as Lanczos algorithm. So Lanczos algorithm basically is well known for the computer science communities and mathematicians, among the mathematicians, to find the largest eigenvalues from some Hermitian matrices. So this Hermitian is important because when we talk about this open quantum systems, this will matter actually. So for example, the operators I will going to talk about all the Hermitians as of now. Okay. So all the Hamiltonians are also Hermitian in this sense. So the Lanczos algorithm starts from actually defining. So the thing is that you expand your time evolved operators in terms of some basis. This ON is now your orthonormal basis, and you want to find this orthonormal basis in using this Lanczos algorithm with some coefficients phi n, which n runs from 0 to k minus 1, when the k is a Krylov dimensions, which is bounded by this your d square minus d plus 1, where d is your dimension of your Hilbert space. So how you start? You set some number equal to 0, and this is the initial condition, and you build. So O is your initial operator, that any operator you take. So there is also some arbitrariness of choosing your initial operator. You have chosen some operator O, and you find this, and you find the inner product using the previous definition that I have talked about, this definition, and you normalize this O0. So this is your initial operator, and you perform your Lanczos algorithm to compute this AN using this O0. For L is again the Liouvillean that I have previously talked about, this commutator with the Hamiltonian, with a set of coefficients. This Bn's will come naturally, the coefficients, and how do you compute the Bn is basically the inner product of this AN. So if you perform these operators, this procedures, the output is that you get a set of coefficients Bn after each step, after performing each step. So for each n, you get a coefficients B1, B2, B3, and you get a set of coefficients. That's that's the main procedure of the Lanczos algorithm. Ultimately, you get some initial operators, and the output is you get some set of coefficients, and we expect that coefficients to tell about how the behavior of the operator. So you can also study a notion of like autocorrelation functions. The OT, you can just take the inner product of this O0 and you get the phi 0. We'll see that this phi 0 also contains the full information about the growth of this operator. So you see this is basically a 2-point function. This is only the 2-point function, whereas this OTOC is basically a 4-point function. So in principle, it is surprising that your 2-point function actually knows about the full growth of the operator. So you might say this operator OTOC may be redundant because it's a 4-point function, and it may not require at all. This 2-point function is enough to give you the full set of growth. Okay. So this phi n's, if you can expand these operators on the phi n's, and you computed this Bn's Lanczos coefficients Bn, and they are related by some recursive differential equations. This equation you can get directly from this Heisenberg equation of motion. So these are recursive differential equations. So these are known as the Lanczos coefficients at the Bn, and these phi n's are some Lanczos wave functions, or kind of simple thing. So you can actually think these equation as some hopping amplitudes. The Bn some hopping amplitude from one of the lattice sides from different in this picture. But we don't need that, of course. So we start from an initial operator. So there's a pictorial. You can start from an initial operator, and it grows over the time. So you have increasing number of growth Bn. So how the Bn behaves with the n, that's the main theme of this approach. So these are the probability amplitude. So they has to be satisfy the unitarity constraint. So basically, this is the probability. This has to be 1, and you define something known as Krylov complexity. This K complexity basically is the Krylov complexity, because you have defined the Krylov space. So this Krylov complexity is nothing but the expectation value of your n, depth n, on the Krylov basis. That's how you define your Krylov complexity. This is a well-known definition of the Krylov complexity, and we'll see this is basically we'll tell about very similar notions about on this out of time order correlator also. You can also define the Krylov entropy. So you have the probability amplitude. You can also define something very similar notion of Shannon entropy. So this is your K entropy. You define a K entropy, and you want to study from some specific model. You want to compute this Bn. You want to compute the phi n's, and you want to compute Krylov complexity, Krylov entropy, and want to study how they grow actually. This everything, okay. So here comes the main part of this. One of the main part of the talk is the universal operator growth hypothesis. So this has been proposed quite recently by this gentleman, and the claim of there is that for chaotic systems, if you have a chaotic system, the Lanczos coefficients, if you compute by this Lanczos algorithm, they grow as fast as possible, and the fast is the linear. So this linearity is they have said that for chaotic system, your Lanczos coefficient should grow linearly with n, with the alpha. With alpha depends on your Hamiltonian and the initial operator you choose. So when you have a Bn like this Bn, you can plug that Bn into this phi n, and you compute the phi n's, and you can compute the Krylov complexity. So it grows out exponentially. It's very similar in the notion of Krylov complexity. Sorry, OTOC, outer primordial correlator. So when you count up chaotic systems, your K complexity grows exponentially. If Bn grows have some sublinear growth. So if Bn grows not linearly but some sublinear growth, where delta is greater than or equals to 0 to 1, then you see that this is a true for an integrable system. And for that case, your Krylov complexity grows at some power-like growth. So by looking at the growth of this Bn's or even the Krylov complexity, you can say whether the system is chaotic or integrable or free, like this picture. So the Bn grows linearly is your chaotic systems, this grows sublinearly for integrable systems, and some order of a number for free fermionic systems, free systems. Okay, so yeah, so that's the main theme of this hypothesis. Okay, so let's talk about this, our old model, this transversal varying model. So we take some initial operator, the same initial operator, and we compute the Lanczos coefficients. So these are the finite size effect I have shown specifically for the finite size effect. So before this finite size effect starts. So you see this is basically a sublinear growth for the integrable system in limit, and you can expect some chaotic growth, some linear growth in the chaotic limit. So this is how you distinguish your how this algorithm works. So this has been done using explicitly implemented using the Lanczos algorithm. Right. Okay. So this is the main statement of universal operator growth hypothesis. Okay. So far so good. So Krylov complexity, an efficient computational measure to detect quantum chaos. And the operator growth hypothesis says that for chaotic systems, the Lanczos coefficients grow linearly, and this is the maximum growth possible. So now you ask the question whether the linear growth always implies the quantum chaos. So remember, the statement is that for the chaotic system, the Lanczos coefficients grow linearly. It's not that all linear, if your Lanczos coefficients grow linearly, the system is quantum chaos. This is not an if and only if statement. So several recent studies by Demarsky and other guys, and also we have also did something that we're going to show in the later slides, that the linear growth of Lanczos coefficients does not always necessarily imply chaos. There may be some integrable systems that can have linear growth of Lanczos coefficients and growth of Lanczos coefficients, and for some specific kind of systems. And so for example, the saddle point, the previous examples that I have talked about, this OTOC, the OTOC also grows linearly, exponentially, if your system has some unstable saddle points. And for the Krylov complexity is also true. So you can say you expected maybe it's a better flow than OTOC, but in this case it turns out that it equally captures in the same thing basically. So
sorry, sorry, Pratik, I have a quick question. So does this behavior that in some cases you don't know for sure whether it's sorry, the linear growth doesn't necessarily mean the system is chaotic. Is there any role of the operator here, or is it operator independent statement?
the statement is the operator independent statement. So if you can choose any operator, so any operator, and it should be should imply this thing. So the operator hypothesis also imply for any generic operator. The only constraint is that the operator is not of the symmetry of a Hamiltonian, because unless the operator is the symmetry of the Hamiltonian, then the commutator goes to 0. H of this commutator. Right? So unless this is the symmetry of the Hamiltonian, it has to be true for any generic operator. So in generally we cannot study for all library operators. We can study few specific operators, and we want to conclude, okay, this is maybe the generic case.
I think Jeff has a question.
And based on your answer for the last question, I have two questions. The first question is, when you say integrable, do you mean strictly integrable in the Yang-Baxter sense of vanishing Lyapunov coefficient, or do you mean not chaotic? So
yes.
I distinguish between integrable and not chaotic and chaotic.
I think in that sense, the chaotic is non-chaotic. There may be some subtlety in that in Yang-Baxter's sense, but in generally also imply integrability by this infinite number of symmetry conserved symmetries, right?
Sure, I take those to be equivalent. But, so when you say integrable, do you mean necessarily integrable in the infinite tower of conserved quantity sense?
In that sense also.
I see. Okay, so that's quite a strict condition. The second question comes from what Sajid just asked. So, how do you see from, let's say, the Altman paper that this should hold for all generic operators? So, for example, if I take a sufficiently large operator, or let me put it another way, if I take a sufficiently composite operator, then even in a free theory, I can see that the OTOCs for the composite operator behave like they're describing chaos. So in some sense, chaos is quantum chaos is a consequence of how you choose to ask the question. That is to say, how you choose to probe the system. If you choose to probe the system with a sufficiently simple operator, which is typically what we think of when we talk about OTOC growth, you take simple phi or psi, and you see how that simple operator grows. But I can take large operators, for example, that span a sufficiently large subset of the Hilbert space, and those operators being large will already start to grow very rapidly. So there's a series of works by the group in the Netherlands. I forget the Jan Zanen and collaborators. I think the first paper in the series is called Operator Thermalization Hypothesis, where they're saying precisely this, that if you take a sufficiently complex operator, and you start with that operator, then computing the OTOC shows exponential growth, even in a free theory, which is kind of a little bit weird, because you'd say, well, what's to interact and thermalize in a free theory? Yet nevertheless, with the standard probes that we use for quantum chaos, you see this. So my question is, how does one see in, let's say, the Altman et al.'s original proposal that this will hold for generic operators, or is it just a hypothesis that it should hold for generic operators?
Yes, currently it's a hypothesis. It's may not be ruled out that you can also rule it out by testing some different operators, also composite operators. But so far this has been done for taking as very simple initial operators. So it's actually depends, this growth of this BN actually depends on this choice of the initial operator. But this proposal is that as far as I understand is how you choose the operator is the information goes into this this alpha, but it should hold for any generic operator unless it's a symmetry of the Hamiltonian. Maybe I need to check about this composite operators for the case. So for any simple one-sided operators for the radar system, this statement is quite strong in that sense.
Great, thanks.
Yeah. Okay. Thank you.
Sorry, I have a question as well.
Yeah.
So the statement that Bn can grow at most or at fastest is going like alpha n. It's only it's basically a system independent statement.
Yeah, system independence, right?
Okay,
Right.
so in the sense that Jeff was just talking about, that we can choose how complex our system is as well. This doesn't depend on that.
Yeah, it should. I mean, the hypothesis states that in principle, because they have given some thermodynamic analogy of this statement also. Maybe some this growth can be understood some thermodynamic principle. So it's basically a system independent statement actually.
Sorry, let me just butt in here for one more second. This statement that the Bn should grow as fast as possible, and that fast as possible being linear, is nothing but a statement of the Lieb-Robinson bound in the space of Bn's. So this defines for you, and you can see it in your plot here, sort of. This defines for you a light cone in the space of in the space of Lanczos coefficients. So that's what that statement is. It's a statement of causality.
Yeah, right. Yes. Yeah. Also. Yeah. This some assumption is there actually. Some localities and causality. I guess there's some assumption is there. So deriving this, I mean, in the hypothesis, I think. Yeah, that's true.
Great. Thank you.
Okay. Sure. Okay. So the thing is that that I've said, let me restate the statement is that this for the chaotic systems, it's the hypothesis that it's the linear, the Bn's grow linearly, but may not be all the linear growth that may not necessarily imply the chaos. Okay, so we'll see the example of here. So this is again the example of this LMG model. So we'll take the same LMG model, and we'll see again if the Bn's are growth again linearly, and the Krylov complexity grows exponentially. This is a log plot, so it's exponential growth. And you also you get exactly precise the match of these coefficients, and basically this is due to the unstable saddle points that leads to the linear growth. It's not due to the chaos. And you can also go to the end of the Krylov space. So this is basically the full set of your Lanczos coefficients. When your Krylov space terminates, your Bn should vanish, and this is also can go to the. So this actually supports the statement is whether even the system is integrable, and you can have some linear growth and exponential growth of Krylov complexity.
Sorry, this may be a very naive question, but I just want to understand this end of Krylov space thing. So in the beginning, you said that the more nested commutators we have, the more an operator will grow, right? So n is basically representing how nested commutators are, right? So having n as 1,000, that's where your end of Krylov space is, right? About
right.
So how many lattice space do you have here? Lattice sites do you have here? And
so
what does it correspond in that sense?
So okay, so this is not the lattice Hamiltonian. So I said this is basically a this Hamiltonian. Just your degrees of freedom is S, the spin. Okay, so the picture that I've showed is for S equals to 25. Okay, so the spin, it's you can think your effective degrees of freedom is 2s plus 1. So that's how you increasing your Hilbert space. So D, that the Krylov space dimension, D that I have shown is basically 2s plus 1 here. So it has to be lower bounded by your Krylov space dimension, right? So yeah, so there is it's not a lattice Hamiltonian, as you said. It's not a lattice Hamiltonian. It's a single Hamiltonian, just a one spin operator, and you increasing your degrees of freedom by increasing the number of spins. So this is for S equals to 25. This blue one is S equals to 25. So your Hilbert space dimension is 2s plus 1. D is 2s plus 1 in that sense.
So in this system, what does operator growth mean?
Okay, so in this system, you are not okay. So this is a good question. So you are not starting from a one lattice site and goes from the 2 and 3 lattice sites. So it is basically you're starting from some same site, some Z, some S operator, and you are taking the commutator with itself. That is the self commutating operator that you can also study how this operator grows. Like for example, For example, in this language, you just start from your same operator, and you can check how this Hamiltonian is not again the lattice Hamiltonian. So as soon as the time evolves, your operator becomes complicated. Complicated in the sense that it's very basically simple at the initial start at the equal to 0, and it becomes complicated. It's not the support of many other operators, but it grows like in your time space, in a time direction. If you have some time direction, it grows in that direction. It's not spatial separation in that sense. So you keep evolving with the time operator by itself. So you can also take some inner product with the s of t with the initial operator s. That's how you grows in that time length.
And the end of Krylov space would mean that the system is not evolving anymore in time.
It goes back to the previous the initial state.
I got you. Thank you.
Okay. Yeah, so because your system has you have a finite size system or your finite dimensional system, your Krylov space has to be finite dimensional. So your BN must stop at some point. This is important. Thanks, Nitin, for pointing this out, because we'll be also encountering this fact in the later discussions. For the finite size system, finite dimensional system, your Krylov space has to be finite dimensional, and your BN should hit 0 at some point, some n. Okay, so you can see, if you go to the classical near the saddle point, that your Krylov complexity goes exponentially. You can see if you have a near the saddle point, your odd and even Lanczos coefficients grows in a very similar pattern. But if you are away from the saddle, your odd and even coefficients have some different growth in this sense. This is basically related to the these autocorrelation functions. So near the saddle, the autocorrelation decays exponentially, but away from the saddle, it is basically oscillatory. That's how the behavior of your BN near the saddle. So using the behavior of these BNs, you can actually determine whether you have a saddle or not in your phase space. So this is just for one example. You can either check another example, and you can also rule out this case also if you find some contradictory statement. But so far, this has been seen in many examples that we did that if you have a near the saddle, your coefficients, the autocorrelation. So the relation between this autocorrelation and BNs are very clear. So if you have near the saddle or near this phase saddle, your autocorrelation, the different behavior of the autocorrelation function will directly lead to the different notion of the saddle. Okay, so we have some analytic computations regarding this, but these plots are specifically numerical. There's no analytic involved. Okay, so the thing is, the autocorrelation functions, Krylov complexity, or the Lanczos coefficients, they can contain the same information basically, but in many different senses. So how you want to understand your growth of the operator, that's how this depends. Okay, so given the autocorrelation function, we can also compute what is known as a spectral function, for example. So the linear growth, so this is basically the Fourier transform of your autocorrelation functions, and if Bn grows linearly, the spectral functions has an exponentially decaying format for large omega. This is how in generic omega should look like. I'll give an example later. So this is for, you see, this is for an example for linear, for a chaotic in general, this is a chaotic behavior of the chaotic system. So they have some linear growth, linear growth of Bn, and the decaying growth of this phi on this omega. Okay. If you have some different growth of Bn for in generic integrable system, except few cases, then your exponent growth of this phi n, you expect to grow more than this exponential. It's maybe an exponential of minus omega square. This kind of, I'll give an example later. So then see that the spectral function also computes also contains the same information about these autocorrelation functions BH, because they are related and they are just a different version of the same thing actually. So this, if you take this autocorrelation function CT, and this has a pole structure also from this upper half plane and the lower half plane, the multiple poles. So you take the first closest pole to the origin, any side. So this class closest pole will give you this precisely the coefficients alpha, this thing. So instead of computing the BNs, if you have the autocorrelation functions directly, you can just do this pole structure analysis, and you can get this alpha, and you can immediately say that how the Lanczos coefficients would behave. Bn equals to alpha n, even if you perform the Lanczos. So all things are related, and your pole structure also gives the information about chaos, because this alpha is basically related to this linear growth. Okay. So I'll give an example. For example, if this autocorrelation is something like, say, hyperbolic t, so this is an example from Mosaic system. So then there is, you can have this Bn is alpha n, and you can compute the moments like this, and they satisfy these differential equations of this kind of equations, and you compute the spectral functions, and these basically behave like exponential minus pi omega by 2 alpha. That's the last slide I have. It's the behavior for large omega, basically for the both sides of your spectral function. Okay. So, and from the moments, from the autocorrelation functions, you can also compute specific kind of moments. So by the repeatedly differentiating this autocorrelation function moments, this is basically the expansion coefficient, Taylor series expansion coefficients of your expansion of your autocorrelation functions, and you find some recursive algorithm like this, and you can exactly find the BNs of this form. This algorithm is numerically unstable, but so you need to take care about when you apply this algorithm. So, but in this, it's a generic algorithm, and if you have a very good feature of your CT, the autocorrelation function, you can directly apply this algorithm numerically, and it will give a good behavior of your Lanczos algorithm. For example, this is an integrable system that I'm showing. It's an Ising model again. It's a critical point. So this is Ising model. So you have, this is not the Ising model that we have talked about. So this is some. This is the same Ising model, but with h equals to 0. Okay, so this is a critical point. This is your ZZ coupling, and there is a X coupling. So you have a critical point. This both coefficients are same. So then you can compute the autocorrelation function of sigma z operator. This initial operator is again matters, the simple operators. So you can compute these operators, and it's basically exponential of t square by 2, and you directly implement this algorithm, and you get a good set of coefficients exactly. The odd and even coefficient is the same. Okay, so you see the autocorrelation decays exponentially, and your BNs are basically very overlapping each other, odd and even coefficients, and you also compute the spectral functions. You see this spectral function is basically omega square by 2. It decays faster than exponential minus omega that previously we have seen. So this omega square is basically showing larger decay than your exponential omega. So it's generically true for the integrable system that it decays faster than this exponential of minus this generically decays what the chaotic system follows. So the spectral function is a very nice feature. This has been so this feature has been studied for a long time actually, but people have been understood in different language, but now they have reformulated the similar notion in terms of this growth of this Lanczos coefficients, which is basically very good actually. Okay, so let me pause a few minutes. If you have any questions, then I will move to the open quantum systems for the next part. If any question. Okay, so let's.
So I just wanted to let you know, Pratik, we have 5 minutes. Okay.
5 more minutes. Okay. Okay. Let's see. Okay, so I'll go a bit quickly there. So recall the definition of the Liouvillean. So for the open, we want to study the similar notion of the open quantum systems. So for the Liouvillean, so we have a definition of a Liouvillean that we have seen previously, and for the closed system, we have some same differential equation like a Liouvillean. Right. But for the open system, they do not follow exactly the same equation. This is known as the master equations. So the von Neumann equations for the density matrices and the Heisenberg equation of motions follow the similar, very different equation with some operators like this. This is basically your the non-Hermitian effect for the environment dissipation effect. So this is your basically the closed system results, and this is how you get from the open system effects. Okay, and this is generically known as the Lindbladian. So previous Lindbladian is nothing but your Liouvillean times your plus added or subtracted the environmental effect. Okay, this has been basically a long time that people have studied for open system in Lindbladian. Okay, so what you want to do? We want to study the same Hamiltonian. We want to take the same Hamiltonian with the same integrable and chaotic limit, and want to study the operator growth in the system. So we take this kind of Lindblad operators. These L's are known as the Lindblad operators or the jump operators. They are basically made of this spin operators, and these alphas actually the alphas and these gammas are actually basically the interaction from the spin and from the system and the environment. Okay, so these operators are made of the spin operators. So these are Lindbladian operators for helicos. These are the some notation, and for example, if your system is a 1 to n, so these operators act on the systems. These dissipation acts on the whole system, and these effects are acting on the boundary of your system. So this is 1 and n at the boundaries. This is some choice of your Lindbladian operator. You can also choose a different set of Lindbladian operators and study how the. So this is basically how you're modeling your system and the interaction with the environment. So, and you want to directly apply this Lanczos algorithm with the Lindbladian, not the Liouvillean, because in your Lanczos algorithm, you see this, the second line is basically acting on the Liouvillean with the initial operator. Now you're acting on the Lindbladian with the initial operator. We need to see what it gives. So when you just directly apply the Lindbladian to the Lanczos algorithm to the Lindbladian, sorry, we see some kind of growth. So we take some integrable limit with this some parameter choice of this gamma, and we have same parameter choice of gamma for the chaotic limit. We see this is basically the closed system effect that we have previously seen, but for the large thing. This is basically the closed system effect. But for the as soon as we increase the environmental effect, this starting grows unboundedly. So this we can compare this growth and this growth. This blue, this is a closed system effect. So this is your linear sublinear growth integrable limit, and this is a chaotic limit. But for when you at some high dissipation, for example, alpha equal to 0.15, you see this for the large n, your growth actually becomes. I mean, both are behaving very similarly. So given only this plot, you cannot say which is coming from integrable limit and which are coming from chaotic limit. And also this is quite misleading, because you expect that Nitin was pointed out at some point that your Krylov, the finite dimensional Hilbert space, you need to have your Krylov Bn should hit 0. So here we take a lattice as n equals to 6. So Bn should hit 0 at some point of time, but they show the unbounded growth. That doesn't come to 0, hit 0. Okay, so there is some problem. The problem is that we are applying a wrong algorithm. So our system is now a non-Hermitian system because the environment is acting, and Lanczos algorithm is basically a algorithm for a Hermitian system. So this is the problem. So we want to find some different algorithm which is suitable for the non-Hermitian system. So it's known as the Arnold Iterations. So from the Arnold iteration is basically you start from a is very similar to your Lanczos algorithm, but now you take this, instead of the previous vectors, you take the subtraction of the whole previous vectors. Previously, it has been dubbed as some full orthogonalization procedure, but it's actually goes beyond the full orthogonalization and is generically applicable to any non-Hermitian system. So the interesting point is that when your system is Hermitian, your Arnold algorithm actually reduces to the Lanczos algorithm. So this Arnold iteration is also studied in many cases for the non-Hermitian matrices to study this kind of diagonalize the non-Hermitian matrices and things. So you just apply this Arnold iteration for the Lindbladian case because it's suitable for non-Hermitian set. So you see you get a two sets of coefficients. So one is basically hk k minus 1. This is a off diagonal elements if you have some matrices made from this H, and there are also diagonal elements. Previously the diagonal elements is 0. You only have off diagonal elements because the matrix is a tridiagonal form, but now we have some also the diagonal elements. So if you want to apply this Arnoldi iterations to this system, you will see this, you get exactly the similar results. So this so this integrable and chaotic limit actually preserved. So you can compute this BNs are basically H k minus 1, this off diagonal elements. The integrable system follow the same irrespective of the dissipation. They follow the growth of this integrable limit, and it follows the chaotic limit. So BNs are in principle are not sensitive to how your dissipation is. It's true for any dissipation. Okay, so Arnold iteration actually keeps the generic nature of the system. That has to be true because at some point it will hit 0. If you go to the beyond side with some precision, it will go to hit 0. But the specific coefficients, this specific kind of specific coefficients actually fails to detect the effect of dissipation because it's true for any generic dissipation. So how this effect of dissipation goes? Now, if you plot the diagonal element instead of this off diagonal elements, you see this has the power to capture the effect of dissipation. So this is the previously all the diagonal elements are 0, but now we have a non-zero diagonal elements. So for as soon as you increase your dissipation, the diagonal elements follows a different trend, both for integrable system and non-integrable system. This is for fixing one gamma, and this is for fixing one alpha. I mean how you manage to model your system for different gamma and different alpha at the boundary. Okay, so thing is that basically this Arnoldi, the diagonal elements of this your Arnoldi. So we call this as Arnoldi coefficients instead of Lanczos coefficients. It's Arnoldi coefficients. So this Arnoldi coefficients actually has the power to detect the growth of keep the dissipation effect, but the Lanczos coefficients, the off diagonal elements, doesn't know about this thing. Okay, even this, and this is true for any non-Hermitian systems. And if you go to the beyond of the Krylov space, you'll see that this actually hits 0 at some point of time. At some point, up to some end. This is what you expect. Because for integrable for any, because your system is finite dimensional, right? So the main theme is that for if you have a system of non-Hermitian matrices, some open system, you have to apply this Arnold iteration, but not the Lanczos algorithm, because that would give some wrong results in your computations. Okay, let's summarize. I'll take just 2 minutes to summarize this. So as the first we studied that the universal operator growth set hypothesis is not an if and only if statement. All chaotic systems follow the linear growth, but maybe all linear doesn't imply the chaos. And also we've seen this 2-point functions, the autocorrelation function, whether this behaves the decaying or is periodic, and they capture all the growth of the information. They are equally powerful at the Lanczos coefficients. And these are 2-point functions. Maybe then computing OTOC may be redundant because OTOC is a 4-point function. However, there are some challenges to compute these Lanczos coefficients. So because this numerically unstable, these algorithms are numerically unstable. So you need a very high precision if you go to the end of the field of space. So you can apply this fully orthogonalization and partially orthogonalization methods to make your system in a finite precision. Okay. However, you can also for this very symmetry of this, you can also leverage the use of symmetry in your systems, and you can also calculate the Lanczos coefficient very efficiently for very specific symmetry. But here we have not used this kind of systems, and we have shown that for the Arnold iteration, basically the correct way to implement the algorithm for the open systems. Okay. So and there's some ongoing works that I'm going to talk about, also some work that I'll be talking about the next talk. So here I only talked about the growth of the operators. What about the growth of the states, operator complexity and the state complexity? So next talk I'm going to talk about the state complexity, because this method is equally powerful to study about the state complexity. So we'll see some few condensed matter systems, specifically how this behaves like something known as weak ergodicity breaking. So you have some some system which thermalizes like chaotic systems, and some integrable systems we do not thermalize, but they are in between. There are some systems which are basically weakly ergodic braking, the same kind of systems, and they are also relevant to the experimental relation. We will talk about these two aspects in the next talk, and we're also going some works on this Krylov complexity in many cases, like for example conformal bootstrap and some scattering metrics. For example, the one powerful example is the sparse scattering. So how do you capture your information of scattering using this Krylov complexity? How complex is your process of scattering? Okay, and we also want to explore some method of moments that I have talked about, how we compute the method of moments from this Krylov complexity. We want to explore some Thermophile double states, SYKs, and the stuff, and want to study something basically known as also in some theoretical aspects of cosmology and probably in astrophysics in some notions, because previously circuit complexity has been also been studied in the cosmology aspect of cosmology, and they have detected the chaos in some de Sitter region to the metadominated region. So here we expect some very similar kind of trend for this quantum information theoretic measure, the scale of complexity. So these are progress with this collaboration that I'm visiting, and thank you for your attention.
Okay. Yeah, we are a bit. So are there questions for Pratik at this point? Let's have some quick questions, and we also have a this Chromospace interaction session. So yeah, the link is on the chat box. So after the questions, we'll log into that. So are there questions? Yes, Ilya, please go ahead.
Thank you very much for the interesting talk. Can you comment on the essentially what you are doing, that I'm not condensed matter physicist or many body physicist, so my understanding, I'm more on open quantum system side, is like you're just looking how quickly essentially the number of your basis states grow if you start somewhere like locally, and you can map it on on the lattice, or you can do it not on the lattice, but that one can argue about that, and you're just looking how quickly the number of basis states are growing. Yeah. And the statement which also Jeff made, that the maximum which you have is like linear because of the I assume neighbor type of coupling. But within the world of Lieb-Robertson bounds, there is this long range systems where you couple not just to neighbors, but next to neighbors, next to neighbors, and so on. Can you beat your linear growth of the coefficients or not? What do you think?
So if you have a so you have a next to next neighbor kind of growth. Okay, so you can take the let me do. So yeah, we have some computation about this Ising model of kind, which is known as axial next to next neighbor kind of interactions. Right? So you have some n into n plus 2 kind of interaction. There you can also do the play the similar role of similar game of this Lanczos algorithm. And you expect you cannot grow more than n actually. So we did some for Ising model case, and we got some sublinear growth. It's not even the linear growth in the system. So that's actually the alpha grows. So this is the coefficient that Bn grows alpha. This alpha actually grows how you model your system, whether this is n to n plus 2 or n plus 3. But I believe this is not going to affect the linearity of this growth as far as the hypothesis. But you can also, this is open to, you can also open to challenge this hypothesis, because the hypothesis is not proved yet. So you can come up with some examples also with some specific kind of operators also which challenges this hypothesis. This can be it will, but so far that I have considered and I've seen even for the next to next neighbor interactions, this hypothesis is valid.
Okay, thank you.
Any other question? Actually, I have a question. So there's this circuit complexity and this K complexity. So in your opinion, how do you compare them? I mean, is there, well, what are the, yeah, so.
Okay, so yeah, so I want to just point out first few advantages and disadvantages of these two things. So the circuit complexity, you just have this choice of the basis set of gates. You need to prefer some choice of basis gates, but here you do not need the choice of basis gates, but you need some need to choose some initial operator and the inner product, definition of inner product. So this ambiguity is still there, but in some disguised fashion. So in the circuit complexity sense, so as I've said this previously, this paper by Roberts, Brown, Susskind, they have computed the similar circuit complexity for a similar lattice system. So they have found that the circuit complexity also behaves very for the integrables in the chaotic limit. The circuit complexity also goes follows this exponential growth, I guess. Exponential growth up to some point, then they saturates at some point. So I mean, again it matters how you define maybe the definition of your complexity in the system, right?
So basically, what I'm confused about is, so I see that the circuit complexity, there's a real limitations in terms of computation, because I mean, most of the prescription is up to quadratic for very nice quadratic systems, right? So it looks like maybe K complexity has more potential in that sense. But then if I look at the spread complexity, even, I mean, operator complexity, I don't know, maybe in principle it's probably doable, but I don't know how difficult it is. But the state complexity, because, you know, if I compare, that's easily comparable to the circuit complexity with the wave function method, Allan-Nielsen approach. So state complexity also has this problem, right? I mean, you have to have this nice, very nice current. You have to start with the current state and so on, right? So I feel like the problems are, in terms of operational perspective, from the operational perspective, are very similar.
Yes, so in general, you can start with any state. If you start with the coherent state, then you can use the symmetries of system and compute things. But you can start generically. You can start with any system. So this spread complexity and operator complexity are basically, we can think is related. It's like if you, for example, if you want to compute the operator complexity of your density matrices, so you can start from your spread complexity for some state. You can do all the computations. You compute the A and B and or whatever complexity you want to find, and you want to find the density matrix. You construct the density matrices from that initial operator, that initial state. So you will get the similar results for the in the operator complexity, because you just basically doubling your Hilbert space in that operator and state mapping. Basically.
I see. Okay. Okay. Are there any other questions? Yeah.
Hi. So yeah, actually, I was about to ask about, about this density matrix formalism. So basically, as you suggested, here we talked about the operator complexity, basically. So I think that would be the next step when we go to the state complexity. So we'll be dealing with the density matrices. In terms of operators, right?
Yeah. So you're meaning this kind of setup or some?
No, for the closed systems only. Yeah.
Okay. So what I just said is that if you can study the complexity, Krylov spread complexity of your that I'm going to talk about next time, is you can start at any state and you compute the Krylov state complexity. But if you made the density matrix from that state, and you do the Lanczos algorithm, follow the same algorithm that I have described today, and you will get the same results. You expect the same results, right? Because this is you just doing the operators, because you can the Schrodinger equation and this von Neumann equation is basically the same, right? This is in this operator language and the state language. So the algorithm that you have to perform the state computation, if you made that state computation directly, you increase the Hilbert space in 2 times, taking the brass states and the Kate state, you expect to the same results for this closed system, that thing, right?
Okay. Yeah. Thanks. Yeah.
And that happens actually. You can at any state and you do this thing, that will happen.
Okay. Sure. Thanks. Okay.
Okay, are there questions? We're almost 15 minutes over now. So if not, I'd say please give a big hand to Pratik for this nice talk. You can maybe mute for a second and just, yeah. Thank you.
Thanks for giving me the opportunity.
Okay, so before